Hey guys, okay, let's get started. This is week 4 recap. So let's start with talking about probability, as that's pretty much what this entire lesson this week was about. I gave you different examples of what probability looked like, so that when you see these things in articles again, you won't be unfamiliar with what you see. You may not exactly remember what it is, but you should be able to vaguely recall seeing it, at least at this time, since we're not going into detail about everything and we're still learning it. Again, you won't catch this overnight, so just be patient with yourself. All right, so probability um, is a complex but essential concept for understanding inferential statistics. We all have an idea of what probability is. You've seen it, you've heard it, you've experienced it, and you've probably done it. Okay, so when you see things like there's an example of, or I'm sorry, there's a 50% chance of recovery, that's probability. Statistically, we can view probability as a system of rules for analyzing a complete set of possible outcomes, or what we often call a sample space. An example of this could be you have two sides of a coin or a six faces on a die. Okay, an event is a single observation or observable happening or outcome, such as the appearance of tails on the flip of a coin, or a 3 on the toss of a die. Okay, probability is the likelihood that any one event will occur given all possible outcomes. Something that you've seen, we use we use a lowercase p to signify probability, and it's expressed as a ratio or a decimal. So for example, given the two possible outcomes for the flip of a coin, the likelihood of getting tails on any single flip will be 1 of 2, or 1 divided by 2, or 0.5. Therefore, we say that the probability of getting tails is 50%, or p equals 0.50. Now, let's suppose that you want to know the probability of getting a 3 when a die is thrown. The sample space is the set of faces on a die, or 6 possible outcomes. So therefore, the probability that you will roll a 3 is 1 out of 6, or 1 divided by 6, or p equals 1.67. The probability that you will not roll a 3 is 5 out of 6, or 5 divided by 6, or p equals 8.33. Now, if someone were to ask you this question and ask for a ratio, the ratio for the probability of throwing a die is 1 to 5. Okay? Because there's 6 faces, so 1 to 5 would be your ratio. This is just an example. And you'll see coin tosses, and die used for a lot of the examples. Now, for any event that is certain to occur, where p equals 1.0, for instance, if you toss a die, the probability of rolling a 3 or not rolling a 3 is 1.0. So in that case, you take p equals 0.167 plus 0.833. That means that these two events are mutually exclusive, okay? They cannot occur together, and they represent all possible outcomes. The purpose of me kind of giving you this background is to simply say that probability is predictive, and it reflects what should happen over a long period of time or over a long run, and not necessarily what may happen for any given trial or given an event. So when you see things like surgeon advises that an operation has 75% probability of success, it simply means that in the long run, for all such cases, there's a 75% of those cases are expected to be successful. Now let's look at probability in a distribution of scores, because all of this ties in together. This should look familiar to you. You have mean, standard deviation. This concept applies. Now suppose you had access to data for height for all adult men alive today. That's millions of scores, okay? That should fall in a normal distribution, which is this normal curve. Now, if it was skewed to the left or skewed to the right, it would not have a normal distribution, right? If it's skewed to the right, that's considered positively skewed. If it's skewed to the left, it's considered negatively skewed. But in this case, this is a normal curve. So, suppose that the mean height is 69. This represents the mean. This x with this line over is the mean. With a standard deviation of 3 inches. 3 inches to the left, 3 inches to the right, within one, and that's considered within one standard deviation, okay? Now, what if you select one man at random from this population? What is the probability that you will select a man that's between 66 inches and 72 inches tall? Or the probability of selecting a man within one standard deviation of the mean. Now, as we talked about in class, you know what this curve means, or you know what this area means that's shaded in greenish. Okay, that 68.26% represents that about 60 out of 100 men will be expected to be between 66 inches and 72 inches tall. Therefore, there's a 68% probability, or p equals 0.68, that any one man that you select will fall within this range, or fall within one standard deviation of the mean. Now, let's say you're curious to see what is the probability of selecting a man 78 inches or taller. That's 3 plus standard deviations and above. And as you see, that's 0.13% or 13%. So 13% of the total distribution equals 78 inches or taller. Again, I'll repeat, probability is meant to be predictive. Okay, it reflects what should happen over a long period of time. Now I want to talk a little bit about something that I think everyone is kind of questioning and having some trouble with. I wanted to give you a different example of what you may often see within your research, or within research in total. Okay, and that is where there are two possible outcomes in a situation, hence binomial. Okay, binomial distribution it's looking at, or I should say, it's appropriate to summarize a group of independent observations by the number of observations in a group that represent one or two outcomes. Those generally are labeled as success or failure, okay? And they are followed by discrete or continuous probability distributions. So just follow me here for a second. So we're looking at how to compute the probability of observing success. And I'm not at right now, it's not super important to go into what the model looks like or how to complete it, but this is what it looks like. It's using factorials, and I'll give you another video that shows you how to do it in case you're curious of how to walk through it. But what I'm more interested in, if you see this in an article, you kind of understand what it means. And I do have an article that actually uses a negative binomial model within their research, and that's this occupational therapy intervention for residents with stroke-related disabilities in UK care homes. So this is something that you can look at, but they actually did use a negative binomial model to look at falls. Again, they wanted to determine success and failures, so they used the model to determine that within what they were looking at. And I have provided that, so that's something that you can look at. But with binomial distribution, it describes the behavior of a count variable, which is x, and it's there are four conditions that generally apply, which is 1, the number of observations for n is fixed. 2, each observation is independent. 3, each observation represents one of two outcomes, that's either success or failure. And 4, the probability of success, which is P, is the same for each outcome. With that, you also consider 3 assumptions. Assumption 1 is if it's replicated, only 2, again, possible outcomes can happen, success or failure. 2, if it's replicated, the probability of success does not change. And 3, replication is always independent. Now, previously I did talk about discrete outcomes. So let's kind of go back, because previously we've only talked about discrete and continuous variables. But just like variables, probability distributions can be classified as discrete or continuous. All probability distributions are classified as discrete probability distribution or continuous probability distribution, depending on whether they define probabilities associated with discrete variables or continuous variables. So, a variable can take on any value between two specified values if it's a continuous variable. Otherwise, it's considered a discrete variable. And here again are examples of what that looks like. Number of children, number of languages that a person knows, and the number of individuals in a classroom. Okay? If a random variable is discrete, its probability distribution is called discrete probability distribution. And I will provide an example of this.